Today we'll be doing our last lesson of Chapter 3, which is 3.6, Polynomial and Rational Inequalities. So we're going to solve polynomial equalities, solve rational inequalities, and then solve problems modeled by polynomial or rational inequalities. So you've seen inequality signs before. It's going to be less than, greater than, less than or equal to, or greater than or equal to, and f is going to be a polynomial function. So here will be the steps for solving, and then we'll apply it. So the first step is the x-intercepts are the boundary points. So you find the boundary points by solving when f of x equals 0. The boundary points are between where the graph lies above the x-axis, which you can see is the blue arrows, and where the graph falls below the x-axis, which is in purple. Above the x-axis is where f of x is greater than 0. Below the x-axis is where it's less than 0. Okay, so first step, express the inequality in the form where you have to have a 0 on one side. So you have to make sure you get everything on one side first. Then you'll solve the equation for f of x equals 0, and the real solutions you find are the boundary points. Locate these boundary points on a number line, and that divides the number line into different intervals. Then you choose one representative number called a test value within that interval and test it. If the value of f is positive, then f of x is greater than 0 for the numbers in that interval. If the value of f you find is negative, then it's less than 0 for all the numbers in that interval. Then you'll write the solution set, selecting the interval or intervals that satisfy the given inequality. And this procedure is valid if less than is replaced with less than or equal to, or you can replace greater than with greater than or equal to. However, if the inequality involves the less than or equal to or greater than or equal to signs, you have to include the boundary sets with the brackets in the solution set. So let's go ahead and apply this. So step 1, we have to first make sure that one side has a 0. So we're going to start by moving the 15 over to the other side. So we'd have 2x squared plus x minus 15 is greater than 0. And then we'll solve the equation by setting f of x equal to 0. So in this step, you pretty much just ignore the inequality sign for now and figure out if you can factor this to solve for the zeros. So if we take 2 times negative 15, we get negative 30. And we need to somehow make a positive 1 in the middle, so that'd be 6 and negative 5. So positive 6x and a negative 5x. Bring everything else down. And now let's see how we can factor that. We could pull a 2x out of both of these. It leaves you with x plus 3. You would pull a negative 3 out of both of these, which should leave you with x plus 3. So we'd have 2x minus 3. Oh, sorry, this should be a 5. My mistake. That should be a 5. And x plus 3, that equals 0. So now you could just go ahead and solve those to see what would our x's be. So let's set them both equal to 0. So this one's easy. It would just be x could be negative 3. The other one would be plus 5. 2x equals 5. Divide by 2. You get x equals 5 over 2, which would be 2.5 on a number line. So those are going to be our x-intercepts, and we will use those x-intercepts as our boundary points. So I'll just start, we have to plot x equals negative 3 and x equals 5 over 2, which is 2 and 1/2. Put 0 here, -1, -2, -3, -4. And I'll plot those points. I'd have -3 as a boundary point, and then 2.5, or 5/2. So the boundary points divide the line into 3 intervals. So our 3 intervals, we have going from -infinity up to -3. Then we have an interval between -3 and 5/2. I'm putting parentheses because these are just intervals we're talking about. 5/2 to positive infinity. So those are the 3 different intervals. And now we're going to do a test value within those 3 intervals and see if we get a positive or a negative number. So between -infinity and -3, I picked -4. So let's go ahead and solve that. Substitute the -4 in for x. You get 2 times 16 plus -4 minus 15, which is 32 minus 4 is 28, minus 15 equals 13, which is a positive. So that means f of x is greater than 0 for all x in that interval -infinity to -3. And again, that's because f of -4 was positive. If it was negative, it'd be less than. So let's try the next one. We have 0 is always a good one to test if you can. So that is in the interval between -3 and 2.5. So 2 times 0 squared plus 0 minus 15 is just 0 plus 0 minus 15. So we have -15, which is a negative. So that means f of x is less than 0 for all x's in that interval, -3 to 5/2. And one more. Let's do the interval between 2.5 to infinity. 3 would be an easy one to try. Replace the x with 3. You get 2 times 9 is 18, plus 3 minus 15. So that'd be 21 minus 15, which is 6, which is a positive number. So that interval is going to be greater than 0 for all x in 2.5 to infinity. Now we'll use that table to help us on the next step. So write the solution set selecting the interval or intervals that satisfy the given inequality. So I'm pretty much just writing what I had in the table. So that's these 3 points here. That's what I got from my conclusions in the table. So now let me make a number line. Now we need to go back to our original to see what were we trying to find. We were trying to find where it was greater than 0. So this is going to work, and this one's going to work. So I'm going to go from -infinity up to -3, and it's a parenthesis, so there's one interval that's going to work. Then the other one is from 2.5 right here up to positive infinity. So that would be the graph of the solution sets that would make this inequality true. Anything in that green is going to make this inequality true. And here's a visual to show why that works. So we have our original here. We need to find where it is above the x-axis since we're looking for greater than 0. So you can see it's above the x-axis from 5/2 to positive infinity, and also from -3 to negative infinity. And so what's in the red would not satisfy the polynomial inequality. Okay, this next one I just provided so you have another example to look at. The first step, they moved the 20 over to the other side. And then they went ahead and did some factoring. And they did actually have a typo in this one that we need to fix. This should have been an X right here, not a 2. So you can see they did it right down here, but they didn't up top. So then they ended up getting these for the boundary points. So they plotted the boundary points, and that gave us our 3 different intervals. Then in the first interval they found we have 10 is positive, so that's greater than 0 in that interval. When they tested the number 0, they got a negative number, so that's where it's less than 0. And this one they got a positive number, so that would be where it's greater than 0. Okay, and this was the original. When you move the 20 over, you end up finding what is greater than 0. So the intervals we found greater than 0 were in this interval and this interval. So that's where the blue interval and the red interval come from. You could also write it like this. These are the intervals where it would make it true. Okay, let's try another one together. So this one, we have a couple things on the other side, so we need to do some rearranging. So we'll need to minus the 1 over and add the 2x over. So we get 4x squared plus 2x minus 1 is less than or equal to 0. Okay, now this one is not going to be factorable. I'll let you know that right away. So we will have to use the quadratic formula, and I'll do that on the next slide. So this is what we're applying the quadratic formula to. This is our A, B, C. So it's negative b plus or minus square root of b squared minus 4ac. You could always do this instead of factoring, but factoring is usually faster if you can. So I'd have negative 2 plus or minus 2 squared minus 4 times negative 1 all over 2 times 4. So negative 2 plus or minus the square root of 4, double negative here, plus 16 over 8. So negative 2 plus or minus the square root of 20 over 8. Now sometimes they'll want a simplified radical, sometimes they will let you use a decimal, so I'm going to show you both ways. So square root of 20 can be broken into a perfect square of 4 and then square root of 5. So you'd get 2 times the square root of 5. So I'll change this to 2 times the square root of 5. So what I have now is negative 2 plus 2 times the square root of 5 over 8, and negative 2 minus 2 times the square root of 5 over 8. Now we could simplify this to a 4, a negative 1, and a 1. Same over here. Negative 1, 1, 4. So we finally get down to the end. We have negative 1 plus 1 times the square root of 5. So I'll just put 5 over 4. And if you plug that into a calculator, you get about negative 0.8. That's one of our x's. And the other one was this one. Negative 1 minus square root of 5 over 4. I'm sorry, this one's the negative 0.8. This one, mixed them up there. This one gives you about 0.3. So our x's are 0.3 and negative 0.8. You would get the exact number if you kept them in radical form. Okay, so if I make a number line here, so we had x is about 0.3, so that'd be right here, and x was about negative 0.8, which is right here. So our three intervals would be, first one is negative infinity up to negative 0.8, or you could put the radical form. Then we have between negative 0.8 and 0.3. Then we have 0.3 to infinity. So if they say to leave in radical form, you'd have to be using the radicals we had on the previous slide. So my three intervals, negative infinity up to negative 0.8. A number that'd be easy to test in there would be negative 1. So replace our x's with 1. I get 4 plus 2 minus 1. Oh, sorry, negative 1. This would be minus 2. So 4 minus 2 is 2. 2 minus 1 is 1, which is positive. So that means f of x is greater than 0. And you would just write in this interval over here. The next one was negative 0.8 up to 0.3. So let's go ahead and try 0. So 4 times 0 squared plus 2 times 0 minus 1, which would just be minus 1 or negative. So f of x is less than 0 in that interval. And the last one, 0.3 to positive infinity. So 1 would be an easy one to try. 4 times 1 squared plus 2 times 1 minus 1. 4 plus 2 minus 1 equals 5, which is positive. So f of x is greater than 0 in that interval. So this was our original. We were trying to find when it was less than 0 or less than or equal to. So the first one, we said f of x was greater than 0 from negative infinity to negative 0.8. So the one that ends up working is the negative 0.8 to 0.3 because we're trying to find where it's less than 0. And the other interval was 0.3 to positive infinity. So if I make a number line here, all we care about is that middle interval. So negative 0.8, and this time we're going to have brackets because it was less than or equal to, up to 0.3, about right there. So this is our solution set. Anything in the red is going to make that inequality true. And here is our visual. This time we're finding where it's below the x-axis since we were looking for less than or equal to 0. So here's our solution set. So they put the radical form, that was the negative 0.8, and this was the 0.3. And you can see they put brackets. That is the interval where it would be true. Okay, now this one has 4 terms, so let's go ahead and move the 4x and the minus 4 over to the other side. X to the third plus x squared minus 4x minus 4 is less than or equal to 0. And now we'll go ahead and factor that if we can. So from this pair we can pull on x squared, which leaves you with x plus 1. This pair we can pull out a negative 4, which leaves you with x plus 1, less than or equal to 0. You'd have x squared minus 4 is less than or equal to 0, and x plus 1 is less than or equal to 0. And then we can go ahead and solve those. Now this one, we're going to end up with 2 solutions on this first one. So if you take the square root, you would get x. So you'd have x is less than or equal to 2. And then negative 2. Now really we could have changed these all to equal signs, so let me go ahead and do that. We don't have to worry about the inequalities right now. So we'd have x equals 2, x equals negative 2. Go ahead and change this. Minus 1, x could be negative 1 as well. So we have 3 different solutions on this one. So let's go ahead and plot those points. So we had negative 2, negative 1, and positive 2. So our first interval is from negative infinity up to negative 2. Then we have between negative 2 and negative 1. Then we have negative 1 to 2. And then we have 2 to positive infinity. So this one has 4 different intervals. So the first interval, negative infinity to negative 2. Then we'd have these other ones. So now let's try to find easy test values we could use. I'll use negative 3 here, negative 1.5 here, 0, and 3. So I'm not going to show all these substitutions because that'll take a while, but I will show you the first one. Negative 3 cubed plus negative 3 squared minus 4 times negative 3 minus 4. That gives you negative 27 plus 9 plus 12 minus 4. So you end up with negative 10. So that means f of x is less than 0 since it was negative in this interval. Then I'll just tell you the next ones. This one you get 0.875, so that's positive, so x is greater than 0 there. This one you get -4, so it'd be less than 0. And this one you get +20, so that interval is greater. Okay, so we said it was less than 0 in two intervals, -infinity to -2, and also -1 and 2. It was greater than 0 from -2 to -1, and from 2 to +infinity. So if we look back at our original, we were looking for less than or equal to. So this is the one we care about. So the way we're going to write this, since there is a equal to sign under it, we're going to say from -infinity up to -2 with a bracket, and the union of that with -1 with a bracket up to 2 with a bracket. So it could include those numbers. Okay, so if I plot that, we would be going from -infinity up to -2, and it is a bracket. So anything in the green would work there, and then from -1 up to 2 with brackets would also work. So anything in the green would make it true. Anything not in the green would not make this inequality true. And here's the visual, so you can see why that there were 4 different boundaries. We're finding where is below the x-axis since we're looking for less than or equal to 0. So -infinity up to -2, and between -1 and 2, that's where it would be true. The red would not be true. Red is not true for the inequality. Okay, then we'll do a rational inequality as well, so this is going to have a fraction involved. And this one, I'll just walk you through step by step. So here is what we're trying to find. So the first step is to express the inequality so that one side is 0. So you can see here they moved the 1 over. That's where they got this step. Now the problem is we need a common denominator. So they tried to figure out what they could put under it. So under it they put this x plus 1, meaning they had to multiply the top by x plus 1 as well. So now they have a common denominator, so that's where they got to this step. So you could leave a 1 in front of that if you want, but it's not necessary. Then they combined it to get this. Then they did 2x minus x to get 1x minus 1 on top. So this simplifies down to this. So it's not going to be much different. It's just going to end up having a fraction involved, and you need to be careful with the common denominator step. Okay, so this is equivalent to what we started with. So we're going to be focusing on this one because it's going to be easier to work with. So we're going to set the numerator and the denominator separately equal to 0, because that tells us where the previous fraction is going to be either 0 or it's going to be undefined. Because if you have the top equal to 0, then the fraction will be 0. If you make the bottom equal to 0, you'll have something that's undefined. So we set this one equal to 0 to get x equals 1. This one equal to 0 to get x equals -1. Now locate those boundary points, so -1 and 1, so we have 3 intervals, -infinity up to -1, between -1 and +1, and from +1 to infinity. Okay, so our first interval, we'll try -2, and when you get that, you get a +3, so that's where it's greater than 0. Our next interval, from here, we'll test a 0, and you get -1. So f of x is greater than 0. And then from 1 to infinity, we tested 2, and we got a +1/3, so that would be greater than 0. Okay, so you can see our boundaries. We have -infinity up to -1 because we were trying to find, again, where it was greater than or equal to 0, so these were the two different boundaries that made that true. So anything in, let me make them a different color, it's a little easier to see. So the only thing that doesn't work is between -1 and +1. We'll end with a application problem. So the position function for a free-falling object near Earth's surface. So here's a formula we can use for it. An object that's falling or vertically projected into the air has its height above the ground, s of t, and feet given by this formula. And then it tells you what each of those letters stands for. Okay, an object is propelled straight up from ground level with an initial velocity of 80 feet per second. Its height at time t is modeled by this formula, where the height s of t is measured in feet and the time t is measured in seconds. In which time interval will the object be more than 64 feet above the ground? So first we'll go ahead and solve this as an inequality. So we want to know when it's going to be more than 64, so that's why we have greater than 64. And we finish solving this. We're going to move this 64 over by subtracting it. You end up getting this. So here's our new formula we're going to work with. Okay, and this is factorable. So if you pull the -16 out, you end up with t minus 1 and t minus 4. Set those equal to 0, and you get one boundary point is t equals 1. The other boundary point is t equals 4. Okay, so on the number line, we have 3 different intervals going up to 1, between 1 and 4 and above. When we test the intervals, we find that the inequality is true, and you can make a table to find this between 1 and 4. So the object will be true for that, more than 64 feet above the ground, between 1 and 4 seconds. But it's not less than or equal to, it has to be when it's more than 64 feet. So you have to exclude the time of 1 and 4 seconds. So you could have 1.2 seconds or 3.9 seconds, but you can't have exactly 1 second or exactly 4 seconds. It's just whatever is in between here and here.